Oh gosh, that's like Siri talking to me. Can't even handle it. Okay, let me go back to that screen. Transfer of heat and the effects of heat. Now, as you know, as plumbers and gas fitters, this is a big part of our job. Why is heat so important to us? Does anybody know? You can unmute your mic and tell me. Hey?
Stay warm.
Stay warm. We live in the damn Arctic, don't we? We live in the north. Without heat, and we all know winter is coming, so to speak. Yeah, we all die. So we live in a cold climate for 6 months of the year, colder, and we need the heat. So this is really important to us. So if you are a highlighter type person, heat always travels from the warmer body to the cool one. Okay, it really does. When I go to bed, and I tell you what, the wife sucks all the heat out of me. It's really crazy. She's got cold feet, and they're like ice cubes when they come in contact. Anyways, heat travels from the warmer body to the cooler body, and that's how we do it. We have no control of the outside temperatures, but we do control how heat is transferred. We have 3 methods. Here's the 3 methods we're going to talk about today: conduction, convection, and radiation. And of course, you probably already know some of this stuff. So conduction basically means touching. When the molecules are together and they're touching, the heat is transferred from one molecule through direct contact to the other molecules. And they get excited, right? When they get heated up, they start to move faster, and they get excited, and good conductors for conduction, it transfers through that body really quickly and really easy. Okay, so this couple of paragraphs, I'm not going to read this to you because I don't want to. But it really is about the transfer of heat through conduction is about touching. It's when something is touching something and it transfers that heat. Now let's have a look at this picture. As you can see, if this block here, if it was copper, and if I heated one end, the molecules will, I need to probably annotate this. The molecules will continue to heat up or move, if you will. As they move, they will transfer all of that heat throughout the entire body. And that is really what conduction is all about. Now look at wood here. You could have a wooden match lit like this, and really there's no real heat transfer in the wood. Is heat a good conductor then?
No.
No, heat is not a good conductor. It is truly not. So conduction is one of the primary methods. So remember we said 3 methods of heat transfer. It is one of the primary methods. They talk about useful application of conduction in a heat exchanger. A heat exchanger is where, let's see if I can, a heat exchanger is where you take cooler water, so cooler water running through a coil, okay? And going out. So coming in and going out. And then you have warmer water coming in and going through a coil. And as a heat exchanger does this, you tend to start to heat up. Let's see if I can do this correctly. You tend to start to heat up this blue colder water as it goes through the heat exchanger, and you get warmer water coming out. So it is the transfer of heat from the warmer body to the cooler body, basically just like that. So this comes from a boiler, this comes from a heating system, and through a heat exchanger, you transfer heat. That's what they're talking about there.
What are you doing?
Say again?
No, I was talking to my cat, sorry.
Oh, good morning, cat. Didn't strike me as a cat person, but that's okay. I have a cat. Really, cats are the most laziest animals I think I've ever seen in my entire life.
Absolutely, just lazy.
They don't have to hunt, gather, nothing. Nothing. The darn thing just poops in a box in my hallway. I don't even know.
That's it. He just sleeps around the house.
And sleeps everywhere. Scratches me when he can't eat or needs to eat. I don't even know.
Yeah, same as mine. Yeah, same thing.
Okay, so we're on that. Okay. I should get a dog. Sorry. Or a mouse or something. Okay, look, on the negative side, look at, there's a negative side to conduction. Now, there's a negative side to every form of heat transfer. The negative side is that this is the primary cause of heat loss in a building. So when we're building buildings these days, the idea is to try to get a very, very tight, what they call an envelope, right? And that's the building shell, so to speak. We want our building envelope as tight and as insulated as possible so we don't lose our heat. But the Alberta Building Code states that we also have to exchange the air within our buildings completely. A half air exchange per hour, I think, is the latest ABC building code. Now, I don't know if I can, let's see if I can annotate this. ABC is the Alberta Building Code, right? And they have a half air exchange every hour. And what does that mean? It means that the air inside our houses, our buildings, where we are, needs to be moving. And we need to take that air out and bring new air in. Now, there's an issue with some of this air coming into our houses and our buildings, is that it gets cold outside, yes? It gets cold. And so Alberta Building Code also says that air cannot be less than 12 degrees C coming in. You can't bring in air less if it's less than 12 degrees Celsius. So, which means for bigger buildings, apartment buildings, etc., we need makeup air units that heat up the air before it comes into the building. The air that we're pumping into our building has to be above 12 degrees Celsius. Now, you ever open a building door on a tall building and the air is pushing outwards? There are positive air in those buildings, okay? So every time you open the door, you can feel the rush of air hitting you. It means that there's a positive air pressure within that building. And they keep it like that so they can keep the heat in, believe it or not. Okay, so that's how that kind of works. Okay, let's see if I can scroll down here. Oh, that thing just stays with me wherever I go. Nice. I don't want it to. There we go. Now, look at this table. This lovely table right here. And it says this material is rated according to the conduction. It's a conduction table, a table of conductivity. So silver and copper are good conductors. Does anybody know why? There's a reason. Does anybody know why?
Purity?
What's that?
Their purity?
Nope. No. I'm going to tell you that it is because of their makeup. It's because they have these extra electrons hanging around them. And these extra electrons, these free electrons, so to speak, tend to move freely through the material. So we use copper as a conductor for electricity, yes? We use copper as a conductor for our heated water, yes? We use it in heat exchangers. We use it a lot because it's a good conductor. So when you push, for example, electrons down a piece of copper wire, it transfers those electrons almost without any resistance. And it's allowed to push it through that copper wire, and it'll transfer all the way down to the end of wherever you have it. That's why we use it for electricity. It's a great conductor. It has that free electron that allows that transfer of electrons throughout that whole piece. Now, look at air. So is air a conductor?
No.
Well, according to this table, air is a conductor. It made the list. It's a very poor conductor, though. Yes?
Fair enough.
Okay, it's a very poor conductor, but we use it all the time, especially in our houses, right? I have a furnace downstairs in my house, and it has this metal box, and I put a fire under this metal box, and I heat up all this air, and then I take a fan and I blow this air around my house, and I'm relying on that conduction of the flame touching this heated box, touching the air to heat my house. It's really super inefficient. It's I'm just blowing scorched air around my house. It's not very great. So I should, or I hopefully have a good envelope or good materials keeping the heat in my house. Now, when I have windows that suck, which I do, I lose a lot of heat out of that because through conduction, I lose all my heat out of my house. How about water? Is water a good conductor? Look at where water is. We use water all the time as well for conduction of heat transfer. And we heat up water and we run it through pipes to heat buildings, right? We put them through little heat exchangers, put fans behind those little exchangers, and we blow that heated water or that heated heat exchanger, we blow the air through it so we can stay warm. So again, look at this. Wood is right there, just below water as a conductor. I mean, I saw a picture up here that shows wood being a terrible heat transfer. But again, it does transfer a little bit. All right. Any questions so far? No?
Wouldn't air be a good insulator too? Is it not?
Air can be an insulator. We put insulation in our walls, right? But it's very porous. It's full of air as well. So yeah, air can be a good insulator as well. As you can see, it's not a great conductor, so we could use it as an insulator. Is plastic a good conductor? No, that's why we actually use plastics as an insulator around our copper wires for electricity, right? It insulates and we can't feel the heat from it. Okay, so the next thing on the list here is convection. Look at this. Convection is the transfer of heat within gases and liquids by different densities. Now, different densities. Hot air is lighter than cold air. Is that correct? Sure it is. So hot air rises. So we use convection to move air throughout the house as we heat it. Water is also has convection currents. So this is the gases and liquids that they talk about. And things float up. Like in a lake, water is warmer at the surface than it is at the bottom, because cold water will sink and warmer water will rise. It's just because they're different densities. Not a great amount of densities, but different densities. Now look at this. Hot air balloons operate on this principle, right? Air is trapped in the balloon, causing the balloon to rise because the air surrounding it is less dense, or excuse me, the air inside it is less dense, causing it to rise. Did anybody see David Blaine with his little balloon trick going up in the air? I mean, it was all over the
Yeah,
news.
I did.
That was pretty. I don't even know. Dallas, are you in North Korea right now?
I'm working on it. I don't know how I
Okay,
feel about
all
Trump.
right.
So.
We'll call you the new Dennis Rodman. That's all. Okay. Now they talk about some old gravity systems, etc., in here about how heat transfer rises. So we used to heat, very old time. We used to have just a big tub of water with pipes attached to it, and we put a fire under it, and we'd heat our houses that way, because just through convection currents of the water, that heat would rise. So if I could draw something rudimentarily, I think I can do that. Let's see. So we would have a big boiler in the basement, or a big cavity full of water, and we would light a fire under it. We would light a fire. There's my fire, so to speak. Okay, there's my fire. And they would use coal, wood, etc. And then what they would do is they would have this water piped upstairs, and it would come back. So as this water is heated, it would go up because it's warmer just through convection currents, and it would heat the other rooms, and through convection currents, it would come back to the boiler to be reheated. That is really the basics of a boiler. And they used to do that without pumps, without circulators, etc., and just through convection currents. Now, having said that, this pipe would have to be very big, 2-inch or larger, to carry those, to carry all that water, right? Because that's all you have. That's it. But that's a very old school, if you will, type boiler. Okay. All right. Let's clear that off. Now, baseboard heaters produce convection currents of the air to spread throughout the room. Yes? Oh, that's really bad highlighting. And then again, forced air furnaces rely on convection to circulate the supply around the house. Okay. Now let's clear all of that. Okay, so there's negative effects. So there's positive and negative effects of convection. So we can get unwanted circulation that can occur. And they talk about a boiler being, or a room being overheated because of convection currents. And there's different controls that we use to stop that from happening. Oh, there we go. Convection currents of a baseboard heater. Look at this guy. He's very chilled, right? Just sitting there. So this pipe right here. So this is a baseboard heating pipe right there with the hot water running through it. And then we usually have fins on that. Is that correct? We have fin baseboard, so we run hot water through there. And just through convection currents, we have this air circulating, right? The cold air dropping down, the hot air coming out, right? So that is just basically clear convection baseboard heating. And that's what we have there. Beautiful. And then we get to the third one, radiation. Okay, radiation Now they use this great term, electromagnetic infrared rays. Okay, that's fine. But heat will transfer on a radiant issue without heating the air in between it. It heats the objects. It's the sun in the sky. That's radiant heat. It does not heat the air, it heats the objects, which then heats up the air. Okay? Really is what it is. So it says that this can travel through a vacuum, and that's the sun, really. Fire pit is radiant heat. Okay, we have radiant heat from a fire because we feel that heat from the flames. It's not heating the intervening airspace because it could be cold outside. We could have a fire and we could feel the heat from the fire. It's not heating the air. Radiant heat, light colored shiny surfaces like my head are poor absorbers or emitters, right? In contrast, dark rough surfaces absorb that radiant heat quite easily. Okay, so your car, inside your car, you ever get in your car and you burn yourself sitting on your seat? I have, right? So kind of like that. So now in the pipe trades, we use radiant heat a lot, yes? So the major advantage of radiant heat is limiting the heat transfer to the air. It's heating the objects. And that's why we love this. We love radiant floor heating. Look at this guy again, right? Great picture. Radiant floor heating. It's not heating the air, it's heating the objects that it comes in contact with. Okay. Now, this is very important right here. 3 methods of transferring heat. Now, there's always the 3 methods happening all of the time. We can't escape that. But just one is more prevalent than the others. So let me just make a note of that. So it all happens at the same time, but one is more prevalent than the other. So when you get a question that what is this conduction, is this convection, is this radiation, you have to figure out which one is more prevalent. That's all, okay? Okay, we're moving on. Now they went to an exercise, and I think I have some of these questions in your exercise that's coming up, and I'm going to skip that. And we get into expansion and contraction. Does anybody have any questions so far on the 3 types of heat transfer? Okay, awesome. Thank you. All right, expansion and contraction. Listen, everything expands, everything contracts. Even you, right? Even you expand and contract, depending on, you know, how you're feeling sometimes. That's just a joke. But listen, all of our materials that we use in our construction expand and contract. You must always be aware of the effects of a expansion and contraction because we can do damage if we don't control it. Now my house is a little older, and when I'm in my bathroom and I run the hot water in the sink, I get this little tap going on. Can everybody hear that tap? That happens inside the wall, that tap. And what that tap is all about is that's my ABS pipe expanding inside my wall when I'm running that hot water through it. And it gets to be, well, it slows down after things still. So if you haven't heard that before in a quiet space, you can sometimes hear it in some older houses. And that's the pipe actually expanding. And it's rubbing against the wood. And I would really, you know, when you guys are drilling your holes in wood, so here, if this is wood and you have to drill a hole to put a pipe through, I'm going to really emphasize that make sure that hole for that pipe is big enough. If you get it in there super tight and just barely moving, it's going to make noise in that piping system, whatever it is. If it's the hot water line, if it's the drain line, if it's the heating line, especially, make sure there's room for that pipe to move within there. I've had many service calls where they complain of noise for their heating. And listen, I go there during the day and everything just running just fine. I see no problem. They only complain about it when they go to bed and the heat comes on, and baseboard heating, when it comes on at night, it will make noise. And if it's really tight construction in the walls with constricted pipe, man, it starts to bang a little bit. So to fix that is arduous. You have to cut open the walls and free the pipe a little bit so it's allowed to move properly. I think in your heating class with Robert, you're going to talk about controls for expansion and contraction on piping systems, specifically heating systems, and how to install and correct that. Okay, I get that all the time, believe it or not. Well, when I used to work for a living, like I don't work for a living anymore. I just sit in my spare bedroom now. Talk about stuff. So as you can see, look at this picture right here. This picture right here shows expansion, contraction of molecules. As they expand, they get bigger. Yes? So as they're heated, the molecules get faster and they assume to get bigger, but they get heated is what happens, right? And it's on a molecular scale, greater. The greater the temperature change, the greater the change in volume, because things get bigger and smaller, really, is what happens. Okay, so this is super important right here, okay? This next expansion, contraction of water. So I'm gonna go down to this picture right here, and we're gonna talk about this for a second. Water does some weird stuff. Okay, so water right here is water is most dense. So it's at its maximum density is at about 4 degrees Celsius or 39 degrees Fahrenheit. Those are two important numbers. Please make note of those. Water is most dense at 4 degrees C. Now that's when water is settled down in the bottom of a lake. That's where it sits, is that heavy, dense water. It's heavy, and warmer water goes to the top. So if you ever dove in a lake and you dive down in a lake, it gets colder as you go deeper. And this is exactly why. So when water is heated, so this is water being heated as it comes up like this, as water is being heated, I'm going to say right here, it expands wow, it's hard. 5% its volume. So it'll expand about 5% its volume as it's heated up to the boiling point. So from here to here, so from here, when it gets up to there, it'll expand about 5%. Now this is the reason why in heating systems we need expansion tanks. We do not want the expansion of this water to take place in the heating system. We want it to take place in an expansion tank. And Rob should explain a little bit more about that later to you. So that's why we need to have an expansion tank. Is water expands as it's heated, yes? And then when water boils, look at that. When water boils, water expands again. It expands 1,700 times its volume when it boils. Crazy. So as we heat water, it expands. And then when we get it past the boiling point, look at those temperatures right here. When we get it past the boiling point, it expands 1,700 times its volume when it goes to steam. Similarly, when we have water down here at its most dense, when it gets colder, look at this, it expands again. Water expands when it gets colder than 4 degrees C or 39 degrees Fahrenheit. It expands more. And it says when, so look, water expands slightly when it gets to 0. And then when it freezes, it expands again. So water expands when it freezes. Water expands when it boils. It's craziness, okay? So those numbers, you need to know those numbers. 7, 5, you need to know, you need to know, need to know, need to know. Okay, water does some crazy thing. And now I have to make a little caveat on this, is that all of these numbers will be at STP. Anybody know what STP means?
Standard temperature and pressure.
Standard temperature and pressure. That is correct. Okay, let's just see what we can do here. Okay, I'm going to make a couple of notes about that because I think this is an important part. We need to make sure we know this, and we know it from first year, but we do need to go. So I know this is a little lagging, but it's okay. Standard temperature and pressure. Did everybody see that screen? Am I sharing that correctly? Nobody can see anything yet. Hang on a second. I got to share a screen here. Here we go. Can you see that? I don't even know what I'm looking at. Can everybody see my screen? It says standard temperature and pressure. Yes? Okay, good. Just, yeah, head shake is great. Somebody wants to unmute their mics and answer at any time, please do so. So standard temperature and pressure. We're going to go standard temperature first. Does anybody know what standard temperature is? Anybody?
20 degrees.
How much?
20 degrees.
20 degrees. That's pretty warm.
15 degrees C.
There we go. It's actually more closely to 15.5 degrees Celsius. Now, next time you are pumping gas for your vehicle, right on the gas pump, right where the numbers come for your payment, it will say just below that, volume corrected to 15 degrees C. Because they want to sell you that fluid, that petrol, they want to sell you that at a standard temperature. Because what happens to the volume of fluid as it's heated. It gets bigger, yes? And as it's colder, it gets smaller, that volume. So they want to sell you that fluid at a standard temperature, so that volume is at a certain temperature. Now, this is why in Canada, our gas containers for our gas pumps are buried underground. So they maintain a standard temperature. Okay, so that's why they do that. Now, and if some southern states, you can have the gas containers actually above ground and in tanks around the petrol station. They could do that. Now, there is a equivalent to that, and that is 60 degrees Fahrenheit is also standard temperature. So all of our calculations that we're going to do all have to be at standard temperature. We're not going to add temperature to them yet, that sort of speak, but all of the liquids and gases that we deal with, we're going to assume at standard temperature, okay? Unless we heat them, and we'll talk about that for sure. Now, pressure. Does anybody know what standard pressure is? Yell it out if you know it.
14.7.
That's correct. So 14.7 pounds per square inch atmospheric. That is the weight of the atmosphere at sea level. So sea level, that is the weight of the air. Now, we need all the equivalents of that. Does anybody know what the metric equivalent of 14.7 psi is?
101.
101 kPa. Now, we also use, unfortunately, mercury as a pressure rating. And mercury at sea level is 29.92 inches mercury. And there is a metric equivalent to that as well. So that is 760 millimeters of mercury is also standard pressure. So what we, now, does anybody know how this came about, this 29.92 inches of mercury, and how they figured that out?
I walked around with a tube of mercury.
That's right. The guy walked around. He had a bowl filled with mercury, and I'm gonna color my mercury green. So, and he had a tube in that bowl, and the tube was closed at one end, but it was open at the other. So he filled the bowl full of mercury, and at sea level, the pressure exerted downwards in that bowl kept the mercury up this tube to 29.92 inches. And then when he went up and down the mountains, as he started walking up and down the mountains with his little tube, he noticed that this mercury level started to drop as he went up a mountain. So there's less pressure, air pressure, at higher elevation. Yes? And this is why my golf ball flies farther here in Calgary than it does in Vancouver. In Vancouver, I feel like I don't know what it is. I don't feel the same. I can't hit my ball nearly as far as I can here because of the air pressure differences, because we are at a higher altitude. Does anybody know what our altitude here in Alberta is?
400.
3,400 feet above sea level for Calgary. 3,400 feet. If you drive straight west on number 1 highway, and if you come to a place called Scott Lake Hill on your way to Canmore, that is used to be, a long time ago, used to be one of the highest highways on the Trans-Canada. And at Scott Lake Hill on your way to Canmore is 4,000, I think it's 626 feet above sea level right there at Scott Lake Hill on your way to Canmore. And now that's why our Rocky Mountains don't look as high as some mountains like in Europe or other mountain ranges. It's because we are on a very high plateau already. So our 10,000 foot mountains only seem about 6,000 feet high. So that's why our mountains don't seem as high in other locations, because our valley is higher than most. That makes sense? Yeah. Okay, there's a little geography, traveling information for you right there. Cool, huh? So this guy that did this particular person that did this walking around, I have a chat issue here. I don't know. Interesting. Yeah, it is interesting. This guy that walked around and did this, he also noticed that when a big storm or, big thunderstorm came over the horizon, that his pressure dropped as well for a storm, right? The pressure went down for a big storm. And when the sun came out, that pressure went back up. So he created a barometer, and he started predicting weather according to his barometer. And this guy's name was Torricelli. I don't know why all those Italians really got really smart, but there it is. So this is the guy that created the barometer, and he also figured out pressures and what standard pressure is at sea level. Okay. All right. Well, that was fun. All those cool looking notes. How's everybody doing? Okay, well, why don't we take a 10-minute break? Just pause there, go get yourself a coffee, a water, whatever it is, stretch your legs, go for a walk. We'll come back at 9 o'clock and we'll continue, okay? Awesome. So I'm gonna mute my camera here as well, because I need a new coffee as well.
Dallas, my man.
Yo, brother.
Nice background, man.
Like it? You inspired me, bro.
The supreme leader.
You ready for this weekend or what?
Oh, fuck yeah. Big time. Big time.
Feel you, bro.
I'm eating now, so.
What are you guys about to say? What are you eating now? It's weird not seeing you eat in class, man.
Scrambled eggs. Every morning. Gotta have my eggs.
Oh, yeah.
Hey, so this is kind of random. Did you guys do that blueprinting review thing?
Yeah.
Yeah, so like I had a question because like the last time we did that review, I got like the depth, like when they're talking about like the orthographic projections, and it asked for like length, width, depth. I fucking like bombed that, and like we got those again there. Do you guys know like where I would find that?
Honestly, bro, I Googled it, I think.
You Googled it?
Oh, fuck. That's in my, that's in the first year common. Do you have the first year books?
I don't have.
I have the not the common. I have the the old school ones. So
Yeah, let me
which,
see if I can find it. One sec.
that'd be sick. Thanks, Daryl.
You're talking about this right here. One sec. Let me take this off here.
Which
Can you see that?
yeah, which ILM is that? That is
Blueprint interpretation.
so that's 106, 105I.
106, 105H. This is what I got. The orthographic dimensions, like when you're looking from the top view, you do the
Yeah. Okay.
page 11.
Yeah,
You have that, Alan?
I do. So like the question was, it was just asking like the
From the
front
top.
orthographic view would show
Height and
length,
width.
length, width, height, and then there's also like a depth.
Yeah,
So there's like
there's the side view and the top view.
depth is the side view
Yeah, and top view.
and top view. Sorry, would it be too much to ask if you could like draw it out and then just like show me what the dimensions are?
Yeah, so I'll just show you on this.
Yeah. Okay, sick.
So this is the side view here.
Yeah.
So your depth is this.
Okay.
The top view, so your depth is this. It's how deep the object goes in, right?
Okay, awesome.
Your width is this, and your depth is this. And then your height is obviously how tall it is, right?
Yeah.
Height, width, depth.
And depth. Okay, awesome. Thank you, man.
Yeah, no worries.
Okay, yeah, because I was just like length, width, and height is what I fucking know, right?
Yeah, exactly, yeah.
Awesome. Thanks, buddy. Appreciate it.
Yeah, no worries.
Eat your eggs. Thanks.
Oh, hey, everybody. How we doing? Everybody's okay? Alive and well? Sean, I love the Goonies picture. I can't. Oh, man. I remember watching that movie, I don't know how many times with my kids. Just crazy. Oh, there we go. Now we got the Cobra Kai. Some of these movies might be a little too old for you. Go back a long time. Yeah. So we've been recording, and I should have paused the recording, but we recorded the entire break. So I have to, I have to apologize for that. I'm going to have to be aware of the recording as it gets when we take breaks and stuff. Well, it's going to be a very long session then, I guess, of this recording. When I post it, it's going to be like 2 hours long. So I'm sorry about that. I completely forgot that it was being recorded, and we recorded the entire break of 10 minutes of silence. So if you are reviewing back this recording, make sure you skip over the 10-minute long break of silence, because that's great to get through. Okay. Okay, is everybody back? I hope so. Is everybody back? Okay. I'm going to start up again. So here we go. I'm going to share a screen. What screen am I going to share? I'm going to share this one. Everybody see my screen about coefficients of linear expansion. Just give me a head shake or something, or some kind of, everybody see that screen?
Yep.
Okay, awesome.
Yeah.
So what this is saying is that different substances expand and contract at different rates. And they give a list of those products, those substances. They gave us a rate. And what it is a coefficient of linear expansion per degree, either Fahrenheit or per degree Celsius. So one is metric, one is imperial, as you can understand. So this is the reason why we need expansion and contraction devices in our piping systems, is because this stuff contracts, right? So we need to know how much, or we need to calculate how much things expand and contract. So I'm going to do an example of that with you. So let me just pull up and I am going to now, can you see the screen with the question on there? Anybody? Anybody? No? Yes? Yes? No? Okay, my sharing screen has been paused. Okay, I gotta reshare. I try to change screens without you guys, and that never works. Okay, there we go. Can you see now the question that I have written out here?
Yep.
Okay. So I have a 70-foot or 75-foot long PVC plastic PVC pipe installed on a cold Calgary day, minus 10 degrees Fahrenheit. So I really want to make the note, if you are working imperial measurement, you are going to have everything in imperial measurement. Your coefficient of linear expansion is going to be in imperial measure. Everything has to match. If it's Celsius, you have to use the Celsius one. Okay. So we got the 75-foot long PVC pipe installed on a cold day. minus 10 degrees Fahrenheit. You put fluid through it at a temperature of 140 degrees Fahrenheit. How many inches will this pipe expand? So the formula we're going to use, I have a formula right here. And this is the expanded amount. And what we do is we take the original length, we multiply it by the delta T, or the temperature change, and we multiply it by the coefficient of linear expansion. So let me write that out. Original length multiplied by delta T, which is the temperature change only, multiplied by the coefficient of linear expansion, and that would equal the expanded amount. So there is the formula for calculating linear expansion of a pipe or a product. So let's do this question. So my original length is 75 feet. My temperature difference or temperature change, I'm going from minus 10 degrees Fahrenheit to 140 degrees Fahrenheit. My temperature change is 150 degrees. Everybody see how I came to that number? It's a temperature change. It's how much that temperature has changed within that piping system. So that's going to be 150 degrees Fahrenheit. And then I'm going to multiply that by the coefficient of expansion. I have it written down over here. So I will take out my calculator and I will type that in. I don't know if you can even see my calculator. There it is. So 75 times 150 times 0.123433 equals. So this expands. The answer is 0.37125 feet. It's important to realize that when we're multiplying these, whatever your original length is in, your answer is going to be in the same increments of measure. Now, the question asked for how many inches. So is that the right answer right now? No. So we need to multiply that by 12 inches in a foot. And that expands 4.455 inches, almost 4.5 inches. So if you have that pipe and you have hangers on it and it's moving 4.5 inches, that could cause some damage. That could cause all kinds of problems within that system. So we have to account for that. We have to make these expansion loops. We have to do something to help this expansion. Any question? I think we need to do one more example.
Where's the expansion rates for the pipes at?
Pipe size doesn't matter. Good question though. Pipe size doesn't matter. This is one thing. This is one time where size doesn't matter.
Okay.
Okay. So the pipe diameter does not have an effect right now on this. We're only talking about the expansion of the outer material within that. So it is per.
So if you want to
expansion
turn
per
that
meter.
decimal into a fraction, you just multiply it by the denominator of whatever you wanted it to be.
Sure. So if I wanted in 16ths, I will take the 0.455 multiplied by 16. And that would be 7. So it's 7/16, 4 and 7/16 inches. Cool. Any other questions before I move on? Okay, I want to do one more example with you of linear expansion. Okay, here we go. I have a piece of pipe right here. And the question says, I have a 100-meter long copper pipe installed at 10 degrees, operates at 90 degrees C. How many millimeters does it expand? Okay, so here's my formula, right? Original or expanded amount equals original length times a delta T times the coefficient. So I'm going to take my original length, 100 meters, and I'm going to multiply it by my delta T. So from 10 to 90, that's an 80-degree C delta T. And I'm going to multiply it by the coefficient of linear expansion for copper pipe. I have it written down here. I took it off that table that we saw in the last thing in the ILM. And that is per degree Celsius. So if I type that out on my calculator, let's see if I can get the calculator shiny, nice and shiny up here. There we go. So 100 times 80 times 1, 2, 3, 4, 5, 171. Ooh, I don't know what I did there, but I got a 0. Okay, let's do that again. 100 times 80 times 0.12345171. I think I'm a decimal too far. Yeah, 1, 2, 3, 4. Because this is only 4. This is only 4. I have the wrong. Oh, that's 4. That's 4. There we go. Let me do that again. There we go. Okay, there's our answer. Is that the right answer?
No.
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 No, it is not. Okay. That's right. I have to multiply it by 1,000 millimeters in a meter. Yes? So that pipe is going to expand 136.8 millimeters. Yes? There is our correct answer. With my mistakes on there. Sorry. Hopefully you can understand that. Any questions so far? No? All right. Let's see. Not sure what screen you guys are seeing right now. Sometimes I'm gonna, hang on, I gotta try this again. Does everybody see my screen right here of the ILM?
Yeah.
Yes, okay. So again, objective 3 exercise within here is asking you to do some calculations. Just practice of that. Now, let's have a look at this. Applications of expansion and contraction. Now, many of the controls in our plumbing industry operate on the principle of expansion contraction. Yes? Expansion operates a mechanism to reduce the amount of heat or not. Now, this picture right here, this picture of this thermostatic steam trap. I'm not sure if you know how that works. So what I'm going to do is I'm going to draw a little picture, if I can, on this. Let's see if I can do this correctly. I'm going to try and share my screen again. Everybody see my little Elmo camera here? So in a steam type system, we will have a pipe coming up, carrying steam, going to, and we will have a valve here. Almost always it's a globe valve going into a steam radiator. Okay. So if we have steam rising, we have steam rising up this pipe, coming into this heat exchanger. Now this could be an old steam convector or radiator, sometimes they call them. It's a couple of different things. So then the steam fills up in here, right? And as the steam heats up in here, right at this location, we have that little steam trap. And what it does is it has a bellows in it with a little plug. And so inside this, going back down, because we have to have condensate going back down to the boiler, as the steam enters here, this has a little hole in it that allows the water to flow through. So when this is heated, it plugs off the hole that allows this to go through, keeping the steam inside this heat transfer unit. Now, the heat transfer unit can be called a radiator, called a convector, can called a heat exchanger, whatever. It's a heat transfer unit, meaning it transfers its heat from one form to another. Now, through convection currents, the cold air comes down and flows through, and the heated air rises off it. And as the steam is giving off its heat, it gives off heat at about 970 BTUs per pound of steam. It will give off its heat and it'll start to condense to water. And once it starts condensing to water, this steam trap that's in here will contract and open up and allow the water or condensate to go back to the boiler. So we use the heat within the system to control a device. And that device that I'm talking about right here, that device right there is a steam trap. I'm going to stop sharing this screen. And I'm going to try and open up my other sheet here. Hang on a second. So this little steam trap, we're back to so this little steam trap, as you see right here, this bellows opens up on heat, closes off this little hole right here, and keeps the steam in. And when it cools down, it contracts and lets the condensate go back to the boiler. Beautiful. Works fantastic. Okay. Now, that's a thermostatic steam trap, and that's how that works. Now, we have this next picture. Can everybody see that bimetal strip? Yeah? Ooh. Okay, that bimetal strip is a principle that we use for controls as well. Because these bimetal strips have a different rate of expansion. I need to draw here. Because they have a different rate of expansion, when it's heated, it'll move one way. When it's cooled, it'll move the other way. Can anybody tell me what kind of device we use that has this principle in it? Has anybody got an idea of what we use?
Thermostat?
Thermostat. I can't draw very well with my mouse. But we use thermostats for this. They're fully automatic controls that we set them and we leave them. And they will expand, shutting off our furnace. They will contract, turning on our furnace. They have a little electrical pulse to them. And when it contracts, it will start the furnace. When it expands as it's heated up, it'll move and shut off my furnace. So it's a fully automatic control using heat in the room to control that particular heating system. Yeah, pretty cool. Except if you live in my house, because if my wife's cold, she turns it up. When she's hot, she turns it down. She doesn't care about anybody else. It's just all about her, which is usually the case, and that's okay. So I've put on my I put a Nest control and I use my phone. So every time she turns up the heat, I turn it down on my phone and she doesn't know the difference. I said, oh, you're still cold? Just put on a sweater, right? Like, just keep the heat the way it is. Don't touch that thing. That's my dial. Don't touch that. Anyways, I'm only kidding. She controls everything in my house. That's just the way it is.
Happy wife, happy life.
Well, something like that. I just want to survive. How's that?
Fair enough.
Okay. So we use heating for all kinds of controls. So one is a thermostat. We have a thermostatic steam trap. We have here we have a rod and tube type. It's another principle that we use for our purposes. And where we have this rod and tube particular type of deal is in a hot water tank. So we have a hot water tank, and as this, let me just, as this is heated up, because this would be immersed in the water, this rod and tube, and as it gets warm, right, it will expand, and as it expands, it will push a disc shutting off the gas valve. And when cold water is introduced into the hot water tank, it goes down to the bottom through a dip tube. So the cold water comes down, and as it hits cold water, this will contract, going that way, starting the gas valve and heating it up again. So we use a rod and tube type principle in hot water tanks. In our conventional hot water tanks that we have everywhere in our houses that you guys install probably on a regular basis. So we use this rod and tube principle, expansion and contraction, to operate our hot water tank. The next here, this picture right here shows an expansion loop. Yes? Look at this expansion loop on this heating system. So this is designed to take the expansion across and through and around, so it does not have a detrimental effect on our piping. So we have in here expansion contraction cannot be eliminated, but by using expansion joints, expansion loops, swing joints, guides, anchors, hangers, we can control it, and we must control it. So anytime you're developing or designing or installing a heating system, we need to take into account for the expansion and contraction of our materials, because we haven't figured out a way to control it by just straight pipe. We have to put in these controls. And now we get to our objective 4 exercises. Here we go. And I'm going to move along now, and then it gets to our self-test, which means we've come to the conclusion of this ILM. Yes? Excellent. I'm going to stop sharing. Do we have any questions on some of this stuff? Okay, so now what I want you to do, this is where you're going to do something for me. Well, not for me. It is for you. You're going to go into D2L. And you're going to go to the assessments. And you're going to go to the tests. And you're going to do assignment number 3. So this is your work to do right now for the next I'm going to give you till 10:30 a.m. today to complete this one right here. Temperature and heat science number 3. Now, it says over here, if you can see my screen right here, 2 people have already completed it. But by 10:30 today, I want everybody to have completed this assignment. It's not very big. It's about 20 questions. 1 hour should be plenty of time for you to do that. So right now, this is what you need to do. Any questions? I am going to stop recording at this time.